Well, good morning. Taking off again here. I'm given tests from 1 o'clock until 9 o'clock tonight, so I'm going to have a lot of time to put stuff up for this class. But among the things I'll be putting up are a new homework assignment on, let's see, we're using sapling in this class. I've got a different homework system for astronomy. And then I'll finally get the groups sorted out for the projectile motion lab. And I'll be posting a film for that. And let's see, what else? The projectile motion lab is partly this week's. Actually, I meant it to be last week, but it took so long to gather the data and stuff. But partly this week's lab, and then it'll be due next week sometime. But early next week, I want to start on a lab that will be giving you a lot of practice with dealing with components of vectors and things like that. And it'll be adding forces is actually what it is. And unfortunately, we can't do it live. It's a nice lab to do in person, and you do some calculations first, and then you figure out what the sum of a couple of forces is. And then on these things we have called force tables, you can hang weights to produce those forces and see if your predictions come out correctly. But we'll do everything except the actual construction part, although I may try to see if I could record a series of short videos where after you turn in your prediction for something, then you can watch the video. And I haven't tried anything like that before, but we may give that a shot. Anyway, we're starting in today with Newton's laws of motion. And Newton's laws of motion deal with forces and things like that. And so one of the things I want to do today is talk about the forces of nature. And there are 4 known forces of nature. Physicists are trying to look at ways where those forces might originate from a single source. And for 2 of the forces, they have managed to do that. They're trying to merge in a third force. And the sticking point that keeps them from trying to get all 4 of them together is gravitation. And so we'll talk about what those forces are. We're not going to go into a whole lot about it for this quarter. Pretty much we'll talk about gravity a fair amount, but for the other force that we'll use this quarter, the electromagnetic force, all we'll look at is the result of it. And one result of it is when you stand on a floor, you don't fall through the floor. That's because of the electromagnetic attraction between the atoms and the floor. So we'll get to that soon. But let's start off with Newton's first law. And I'm going to share my screen over here too. I guess I forgot to open it as usual, the IPvo thing. Okay, now I can share it over there to screen 2, and we'll see what happens when we do that. Do you see the IPvo screen with a bunch of writing and paper and a pen and a calculator, or did something else show up?
I see it.
Okay, good. Wasn't positive when I open it later. And I'll pull some fresh paper up here. So don't want to frighten you with what we're doing in 3rd quarter engineering physics. Just deal with that. Newton's first law of motion is one that was stated almost exactly in its current form by Galileo. And we tend to call it Newton's first law because Newton took it and a couple of other observations about nature and put them as a whole set of things. And when people do that, we tend to call them their laws. Another example of that is in electricity and magnetism. There are these 4 laws that we refer to as, let's see, Maxwell's equations. I was trying to think of the individual law names, and the individual law names have names like Gauss's law for magnetism and Gauss's law for electricity, and Ampere's law, and Faraday's law. So they each have their own names, but together we call them Maxwell's equations. He's the one that kind of tied them together and expressed them in a different mathematical way, so we do that. But here's a way that Galileo kind of came up with the law. Now, at the time of Galileo, and even for a while after that, people thought that the physics that was correct was that of Aristotle, the ancient Greek, and he lived, I don't remember how many hundred years BC, like 400 BC, somewhere around that time. And I read one book that said he was not a man to whom the words "I don't know" ever came, apparently. He had an opinion on everything, and people took what he said about stuff and said it must be right. Aristotle said it, even though he never did anything to test his ideas, for instance. And I think it's to Aristotle that we have the idea that, things like the number of ribs in people and the number of teeth and stuff like that. And he didn't count enough samples to verify all of the things he said. He also said at one point that the speed at which an object falls is proportional to its weight. And I have a demonstration that I do out at school. I wouldn't do it with a physics book, but what I would do it with is an old catalog. And I drop the catalog all by itself, and it hits the floor with a pretty good wallop. And then I take and rip a page out of the catalog and drop the catalog and the sheet of paper. And sure enough, that catalog still falls faster than the sheet of paper. But then I just take the sheet of paper and wad it up into a little ball. And then I drop the ball and the catalog, and they both hit the floor about the same time. The catalog falls just a little bit faster. But I did nothing to change the weight of that sheet of paper. All I did was wad it up. And so just like that, you can disprove what Aristotle said about falling objects. And Galileo was an experimentalist. He comes along in the late 1500s and early 1600s, and he wants to do experiments. And so he does, to test the ideas, some of them of Aristotle, and he immediately finds out that they're incorrect. And so he starts trying to formulate his own things. And so he's already got a tendency to be skeptical about anything that Aristotle says. So he just kind of crosses Aristotle off his list as far as he's concerned. And we'll look at Galileo, Galileo. There we go. He's somebody who was known by his first name. His last name was Galilei, and I'm not sure just why we know him that way, but it happens once in a while. It also happened with a Danish astronomer named Tycho Brahe, and we know him as Tycho because that's the way he wanted to be known. Yes. Anyway, Galileo did experiments with rolling things on inclined planes onto smooth surfaces. And the way he would make inclined planes was there was all this intricate woodwork that he'd have done. He was working in the courts of wealthy people, sometimes royalty in Italy, the Medici family and others that he worked for. And they had money to spend on their favorite mathematician because he would cast horoscopes for them that always kind of flattered them. And so that's the kind of guy you want to support. And so anyway, he'd do these experiments. And at the time of Galileo, something Aristotle had said was that In order for an object to move, it must have a force acting on it continually. So Galileo thinks, is that true? And so he starts doing experiments. And you can imagine Galileo going out on the lawn in front of the Medici Palace and playing bocce ball or something like that. And if you roll a bocce ball across the lawn, as soon as you stop exerting a force on it, it starts slowing down and it'll come to a stop. That would seem to prove that Aristotle's correct. But Galileo starts doing more experiments, and he comes up with spheres that are more uniform maybe than a bocce ball happens to be, maybe a polished metal sphere or something like that, and rolls it onto smoother and smoother surfaces until he gets to a point where he's rolling something onto the floor of the Medici Palace, and this nicely polished floor that's been very carefully made, and it'll roll practically forever. And Galileo is one of the first people who comes up with something called a thought experiment. He does the experiment as perfectly as he can, but still he recognizes it's short of perfection. And then he thinks, what if I could make this perfect? What if I could have an absolutely perfectly smooth floor and an absolutely perfectly round ball? Then that ball would go forever. And so Galileo comes up with this idea that we now call Newton's first law of motion, but he says this: in the absence, or it says this, of unbalanced external forces, an object will remain at rest or in a state of uniform motion. Now, I'm using language that, well, for one thing, it's a language Galileo didn't know. I'm writing in English. Galileo either wrote in Italian or Latin. He could do both. And I'm using some modern terms that he might not have used. But this is the essence of what Galileo said and what we now call the first law of Newton, Newton's first law of motion. In the absence of unbalanced external forces, an object will remain at rest or in a state of uniform motion. Now, we have to define some things. We haven't even defined forces yet, but we'll get to those. Remain at rest, that means the object is just sitting there. And so no surprise with that one. A state of uniform motion, that means constant velocity is what it means. No acceleration. It means it's going with constant speed in a straight line. That's what it means to have constant velocity. So that means if something is not undergoing uniform motion, then there must be an unbalanced external force acting on it. Okay, well, we haven't even talked about forces yet. A force you can think of as a push or a pull. Okay, something that acting alone could make the object accelerate. Okay, so if it was the only thing acting on there. Now, as far as the external part, it has to come from outside. Okay. I don't know if anybody's ever had to push start a car. It's hard. I don't even know if you can do it with an automatic transmission. Maybe you can, but back when I was going to college, I think for quite a while, the only cars we had manual transmissions where you push in the clutch and, you know, have a gear shift and do all that stuff. And they were more expensive. They actually tend to be common everywhere in the world except North America. And so It's just the way things happen to be, I guess. But anyway, you could push start one of those cars. And sometimes in the wintertime, if our car's battery wasn't the newest thing, and as a college student, you don't tend to buy brand new batteries all the time. You get as much as you can out of the old one. If the battery was dead sometime, especially in the winter when it was cold, you could push start the car. And when we lived in Cheney, we would park our car on a downhill slope. And if the battery was dead in the morning, big deal. You just put the car into neutral, have somebody push it from behind. And when it gets up to, maybe 10 miles an hour, while it's in neutral, you have the clutch pushed in. You'd put it into gear, pop the clutch is what you do, and popping the clutch would have the effect of turning the engine over, which is usually the job of the battery to do, but you steal energy from the motion of the car to turn the engine over, and that'll start it up when your battery's too dead to do it. So that's what you used to have to do. However, you could not get the car to move if you were sitting in the driver's seat. As hard as you wanted to push on that steering wheel, the car wouldn't move when you did that because you were not an external force. You have to separate yourself from the car and stand on the ground and then push on the car. So you're not a real part of the car in that case. You're an external object, or you're attaching yourself to the external world when you do that. So that's what that means by an external force. Similarly, you cannot lift yourself up by your bootstraps. That's a really old saying, but say you've got long shoestrings on your shoes, you can untie them and try pulling on those things. And no matter how hard you pull on those shoestrings, you're not going to lift yourself off the ground and go up to the ceiling. So that's an internal force. You're part of the object. You're trying to apply a force to another part of the object, and you just don't go anywhere. So got to be external. And then the unbalanced part, okay? You can have lots of forces acting on things, but like right now, my calculator's sitting on my desktop here. Gravity is acting on this thing. I know that it is, but it's not going anywhere. Gravity's pulling down on it, and it doesn't go anywhere because at the same time, the piece of paper that it's sitting on is pushing up on it. And those forces are balanced, and so it doesn't go anywhere. If I just bring a little screw over here, that screw isn't going anywhere. It rocked a little bit when I put it down, but right now it's going nowhere. Gravity's acting on it, pulling it down, but the piece of paper is pushing up on it, so it doesn't go anywhere. I know that gravity's acting on it because if I just lift it up a little and let go, it drops toward the paper. And so, yeah, gravity was acting on it, but it was balanced, and so it just sits there. So that's something that we have to take into account. Now, this idea of uniform motion. Okay, objects can travel in uniform motion, and I can make my calculator travel in uniform motion, but right now I would have balanced external forces on it. There's me pushing on it, there's friction that's opposing that push, there's gravity pulling down, and there's the tabletop pushing up, and those are all balanced forces, and it'll go in uniform motion if that's the case. But if one of those forces gets unbalanced, like if I give it a shove and take my finger off of it, it came to a pretty close or pretty rapid stop because the friction is still acting on it, and that slows it down and stops it. So to have something in really uniform motion, you have to somehow cancel out the forces along the direction of motion. With this, it'd be hard to do, but I don't know if anybody's ever played air hockey before. An air hockey table has almost no friction on it. It has a little, but you have these plastic discs that sit on this table, and the table has a zillion little tiny holes on it, and air is pumped through those holes. So the air hockey puck is floating on this film of air, and with that, you just give the air hockey puck a little tweak, and it'll go all the way across the air hockey table and bounce off the other side and come back. So there you can kind of see Galileo's law here, or Newton's first law, things going in uniform motion. Now, another way of stating this first law of motion is to say, let's see, yeah, I'll be using that one later. In the absence of unbalanced external forces, an object, whoops, got to spell object right, this is a simple way of putting it, but an object will just keep doing whatever it is doing. And when we say this, one of the examples of doing whatever it's doing, it will remain in uniform motion. And so that's another way of saying Newton's first law of motion. Now, there's a word that we sometimes use to describe the tendency of an object to keep doing this, and the word is inertia. We say that an object that is at rest has inertia, and you need a force to overcome that state of rest. Or an object moving has inertia, and it takes a force to overcome that moving inertia and stop the object or speed it up or change its direction. So we put a number on inertia and we call it mass, but we'll put that off till we get to Newton's second law. Now, there are situations where you need to keep Newton's first law in mind, and some of them seem kind of goofy, but they can be explained by Newton's first law anyway. One of them is, this is an odd example, but imagine that you're in a parking lot, one with all those rows of parking spots, and you're driving around in one, and you're going to have to make a turn to go from one row of parking slots to the next row. And sitting on, this is looking down from above on your car. And so here's your back window, there's your front window. And sitting on your dashboard is something that's a little bit slick, like maybe a sunglasses case or something like that. And you start to make the turn, and the front of your car, now your car isn't at rest, it's moving along here. The front of your car is going to be pointing in this direction pretty soon, and that front corner of the car that was here is going to move over to here. Well, what can happen in a situation like that is that your sunglasses case will tend to keep going in a straight line, and it ends up over on the right side of the dashboard. And people will sometimes say, oh, a centrifugal force acted on it to make it move over there. That's nonsense. The centrifugal force is actually fictional. We invent it to explain the motion of things sometimes when they're accelerating. It's the car that's accelerating. It is changing its direction of motion, which changes its velocity, so it's accelerating. The sunglasses case is just following Newton's first law. It's remaining in uniform motion, traveling straight ahead with the same speed. and the car turns underneath the sunglasses case or out from underneath it, which slides over there. You could do the same thing if you put something slick on the hood of the car and then try to do a sharp turn, or the roof of the car. And when the car makes a turn, the object will keep going straight ahead and fall on the ground. And you see lots of junk in parking lots that apparently that happened to. So that's an example of Newton's first law. It's just the sunglasses trying to keep going in the same direction. Similarly, if you have the car going at a good, maybe you're driving 40 miles an hour and, or let's see, if you're on Highway 17, you could be going 50 miles an hour, and the light turns yellow in front of you, and the person in front of you is maybe a little more cautious than you would be, and they stop real soon, so you have to stop even faster, seems like it. And if you've got a bunch of junk piled on the passenger seat next to you, that junk will end up on the floor of the car. Well, the car is stopping. It's got a good amount of friction between the tires and the road. That's what lets the car stop. But between the stacks of books that you've got on your passenger seat, there isn't as much friction, and they'll just slide off each other, maintaining their constant velocity. They just keep what they're doing, moving along at 50 miles an hour. And as the car slows, they don't. They keep going and end up on the floor. So that's Newton's first law. Where you really need to worry about it is in the wintertime. And let's suppose that you're driving your car down a road in the wintertime, and it's maybe, I don't know, January or something like that, and you're out in the country and you're on a road that curves like that. And so here's your car, and maybe this part of the road here is shaded, like by some trees or something like that. This part's in sunshine, this part's in sunshine. And right here, there's ice on the road. Okay, now, in order for you to slow down to make the turn, you'd have to put the brakes on your car. Now, that's just an internal force. What it does is you push on the brake pedal through some internal mechanisms cause either a brake shoe to expand against a drum of the wheel, or brake discs to clamp down on the rotor in the wheel. But at any rate, they're internal forces that will make the wheels slow down. And so that's something that happens. However, that doesn't stop the car. That just makes the wheels slow down. The wheels depend on friction between themselves and the road in order to stop the car, because it takes a force to slow a car down, an unbalanced external force. And guess what there isn't much of when you're on a patch of ice? Your car will tend to keep doing what it's doing. So if you reach this point and are trying to slow your car down while you're on the ice, your car will just go straight ahead. And it keeps going with constant speed and direction. That's uniform motion. That's constant velocity. And it goes off the road. And every spring you see if you drive around the state, you see all over the place where people in the previous winter had been driving in such a way that they hit the guardrails pretty good, hard enough to damage the guardrails, maybe go right through them, stuff like that. That's what happens on slick roads. You need to keep Newton's first law in mind all the time when you're driving on that stuff. And that's just the first law. Okay, here's just some thought ideas. If you give a book a shove so that it moves across a tabletop, it slows down and comes to a stop. How can you reconcile this observation with Newton's first law? Well, that book would remain in uniform motion if there was no unbalanced external force acting on it. So if it stops, there must be an unbalanced external force. Well, what slows something down when you shove it across a tabletop? My calculator stopped. Okay, it's friction. Now, we'll study friction a bit later, but for now, that's what stops it. Let's see. Joe Cool has fuzzy dice hanging from the rear view mirror in his car. Haven't seen fuzzy dice lately. I guess you can actually get tickets for having those because they obstruct your view of the road. In most states, you can anyway. Why do the dice appear to swing backward when his car accelerates forward? Well, think about this. I'll try to just draw. Okay, so here's the top of the car, or this is the rear view mirror or whatever in the car. And the fuzzy dice are hanging down here. I'm just going to try to draw one fuzzy dice, not sets of them. But this would be looking at it, I don't know, from the wrong angle, I guess. I should look at it like this. So here's the mirror. Here's the fuzzy dice hanging here, looking like that. And the car accelerates forward. Okay. The fuzzy dice will have inertia. They weren't moving at first. And so it will take a forward force to make those things accelerate forward. But for a little while, they'll appear to swing backwards. It's actually the car that's moving forward, and the fuzzy dice aren't going anywhere at first. And then once the car is moving forward, they'll kind of swing back to a vertical position once the car is going at constant velocity. But if the car is accelerating forward, the fuzzy dice are going to have to go along somehow. But what you'll see under those circumstances is that they'll hang at an angle while the car is accelerating forward. And it turns out, in order for this string that they're hanging from to pull them forward, that strings exert a force that's right along their line. Okay, but that string force, which we call tension, will have to have a forward component if it's going to accelerate the dice forward. But it's the string that has to accelerate the dice along with the car. So we have that. Let's see, that's more of a Newton's second law question. Might get to that one tomorrow. Let me talk about the forces of nature here real quick. And this is something that I never even heard of these things until I got farther along in physics. But there are 4 forces of nature, and 2 of them we're not going to have to even think about. However, here's what they happen to be. Well, the one that we're kind of most familiar with is gravity. And I'm going to name each force, list what it acts on. Actually, this would be better if I did it sideways on a piece of paper. So grab a piece up here. And I'll even make a nice table. So all right, and some of the crucial details about the forces. Okay, the name, what it acts on, and its range. Okay, so we'll start off with this. Well, let's just start with gravity. That's one that everybody's familiar with. what it acts on is anything with mass. So we haven't learned what mass is yet, but it's the number that we put on the inertia of the object. The number that we assign to something that tells us how hard it will be to accelerate, to change its direction if it's already moving, and so forth. And again, acceleration means speeding up, slowing down, or changing direction. And the gravity force acts on anything with mass. So, and its range is infinite, as far as we know. We can see out into space, we can see light year or galaxies that are hundreds of light years apart that are exerting gravitational, hundreds of millions of light years apart, I should say, that are exerting gravitational forces on each other. But that force gets weaker with what we call the square of the distance. And what that means is you take whatever else gravity depends on and you divide it by the distance between those things squared. And so that tells us how it gets weaker with distance. That isn't something that we'll have to worry about just yet, so don't worry too much. The electromagnetic force. And we have it tied together into a single force, electricity and magnetism, because starting in, the 1820s, physicists discovered a series of phenomena that linked electricity and magnetism. And then when Einstein came along with his special theory of relativity, he sort of did the final linkage between electricity and magnetism. So we just call it the electromagnetic force. Sometimes you can treat it individually, electricity or magnetism, but they always end up being linked eventually. And what it acts on is charged objects. And we're not going to study electromagnetism except to take advantage of some of its overall effects. So charge objects are things, electrons are charged, protons are charged. Those are the common charged objects. And then things that are made up of electrons and protons, if they have an imbalance of one or the other, they will be charged. And so that's it. But there are actually lots of particles other than protons, neutrons, and electrons. They just don't hang around very long, but they would be acted on by that electromagnetic force. And this thing also has an infinite range. And it depends in the same way on distance that the electromagnetic force does. It's another 1/r² force. So that's nice. Well, there's more to it. One of the things with the electromagnetic force, a phrase that arose with it that has stuck around is a phrase where you say opposites attract. Okay, things that are oppositely charged will attract each other. An electron is attracted to a proton and vice versa. Those are things that are oppositely charged. Something that has an excess of electrons and is negatively charged will be attracted to something that has a shortage of electrons and is positively charged. So that will attract things. Most things have a balance of charge. They'll have the same number of electrons as protons, at least pretty close. But if you have things that have an excess of one or the other, then they become charged. All right, so that's the electromagnetic force. Now, besides the opposites attract thing, something else about the electromagnetic force is that like charges repel. Two electrons will repel each other. Two protons will repel each other. Well, something you probably learned about at some point was that atoms have a nucleus, and in the nucleus there are protons and neutrons together in a very small volume of space. The size of the nucleus is such that if you could blow it up to the size of a basketball, the electrons would be a mile away in every direction from that basketball-sized nucleus. And so it's tiny compared to the atom, but those protons are crammed together in there. Turns out the nucleus is on the order of 10 to the minus 15th meters, up to about 10 to the minus 14th meters. So tiny, tiny volumes of space, but the electrons or the protons somehow stay together in that nucleus. Well, they're held together by another force of nature that we call the strong nuclear force. And it's strong enough to overcome the electromagnetic repulsion between those protons that are in the nucleus. It also acts on neutrons. Now, what the strong nuclear force acts on, it acts on protons and neutrons. Those are the things you've heard of before. Protons and neutrons. And other hadrons. Hadrons are things that are made of more fundamental particles called quarks. And it turns out protons and neutrons are made of quarks as well. And there's something you probably didn't know. We're never going to deal with the strong nuclear force in this class, so you don't have to worry about this. There's a whole zoo of elementary particles, hundreds of different types of hadrons, for instance. And it can get really confusing trying to keep track of all those things. Now, the thing about the strong nuclear force, it's a short range force. Okay, its range is about 10 to the minus 15th meters. Okay, well, that's pretty short range. It doesn't even reach all the way across a large nucleus. And so large nuclei like uranium and stuff like that, the protons on one side won't feel the nuclear force of the protons on the opposite side of the nucleus. They'll still be repulsed by the positive charge over there, but they won't feel the strong nuclear force. And that has the effect that as nuclei get larger and larger, they become more and more unstable. And in fact, every element beyond lead on the periodic table is somewhat unstable. It will eventually decay. And so that's something that happens. And again, we're not going to mess around with this one. We'll just accept the fact that the nuclei that we deal with are all going to stick together for us and not have to worry about that. And then there's another force called the weak nuclear force. By the way, sometimes you'll just hear the strong nuclear force referred to as the strong force and the weak nuclear force referred to as the weak force. And that's just short for that thing, because there isn't any other force that's called the strong force, and there isn't any other force called the weak force. So sometimes we leave out the nuclear there. Let's see. The weak nuclear force only acts on particles called leptons. And there are just 6 leptons. One of the leptons is the electron. And another one is the neutrino. There are 3 types of neutrinos. And I'm just going to say et cetera. I'm not going to worry about it. The name of the 3 leptons are the electron, the muon, and the tauon. And the neutrinos are called the electron neutrino, the muon neutrino, and the tau neutrino. And so those 6 are the leptons. And those are the particles that are acted on by the weak nuclear force. The range of the weak nuclear force is very short. A nice precise term, but its range is about 10 to the minus 18th meters. Okay, now a meter is about as long as your arm, roughly. 10 to the minus 15th is actually a millionth of a billionth of a meter. Okay, this very short range is a billionth of a meter. And so these things are very short range. When I was in graduate school, we had intramural teams the graduate students did for softball in the spring and summer and hockey in the winter. And we called our team the weak force. And nobody ever knew what we were talking about. At least nobody that we played. We played, you know, business majors and every kind of major for their team. And we actually weren't that bad. We weren't one of the top teams in the league because most of us didn't play baseball or hockey in high school or anything like that. We just played it for fun. But once in a while, we'd win a game. Actually, in softball, we usually won most of our games anyway. But all right, those are the forces of nature. And the only ones that we're going to actually deal with much are the gravitational force and the electromagnetic force. We will have a little bit of a unit on gravity. And but for the electromagnetic force, it's what holds stuff together. And so we'll talk about a tabletop exerting an upward force on an object that's sitting on the tabletop. Okay, well, that's the electromagnetic force, and it's really complicated because it's an interaction between every atom in the bottom of the cup here and every atom that's underneath it in the top of the tabletop, and there's a zillion of those things, but we just lump all of that together and call it the normal force and say it's the upward force that the table exerts on the coffee cup or something like that. And that's as complicated as it's going to get for what we do. It's also responsible for friction, and we'll talk about friction, but in a simplified way. So we just won't worry about that very much. And gravity, most of the time, we'll just say the gravitational force acting on something is its mass times the acceleration due to gravity, and go with that. Okay, we got 3 minutes left here, and I'm just going to briefly introduce Newton's second law. We wouldn't bother counting them if there was only one, so now, in order to introduce this, I'm going to have to introduce the idea of mass. And this is someplace where problems could arise. We're going to use the letter M to stand for mass. But usually when we're doing that, we're using it in some equation form where we're just talking about the general quantities of things and not talking about their dimensions yet. And it's when we start putting numbers on things, then we'll deal with that. But we'll use the letter M for mass. And that's just a measure of the amount of material in something. And it's a measure of how hard it is to accelerate. And it depends on, for the most part, depends on the number of protons, neutrons, almost entirely on those two, and electrons. Now, the number of electrons and protons is almost always very close to equal, but the protons are about 1,750 times as massive as the electrons, and the protons and neutrons are almost identical in mass. So the electrons at best will account for about 1/3500th of the amount of mass of an object. So not very much, and we don't have to worry about that. But that's what mass depends on. It is not the amount of space that something takes up. That's the volume of it. you can have a relatively small number of protons, neutrons, and electrons that take up a large amount of space, like in a styrofoam ball. But that same amount of space could be filled with lead and it would be much more massive, or it could be filled with gold and be about 50% as massive as that, 50% higher in mass than that. Gold is actually about 50% more dense than lead happens to be. So that's mass anyway, and what it depends on. So try to remember this, that's what it depends on. But here's Newton's second law, and I like to write it this way. The acceleration of an object, that'll be A, is equal to the force, the net external force, and we write that typically as F net. It's what you get when you add all the forces acting on it together as vectors, divided by the mass of the object. Now, I like to write it this way because the acceleration is usually the end result of applying a force, a net force, to a mass. Where you see this written more often is to write it this way, that F net equals MA. And people sometimes tend to think that, okay, you have a mass and you give it an acceleration and that produces a force. It's the other way around. It's the force acting on the mass that makes something accelerate. And that's Newton's second law. And we'll talk more about that tomorrow and go into some more detail talking about things. So, but there's our first look at Newton's laws, and we just looked at the first and second laws today. Tomorrow we'll maybe mention the third law, although we'll be spending quite a bit of time on the second law still. But those are Newton's laws. If I get enough junk done with online things while I'm giving tests for 8 hours the rest of the day, I'll start diving into grading your tests. And I think one assignment that I'm going to have for sure is this coming week. I'm going to have about 3 assignments where you have to turn in a single multi-page PDF file. And because it's a real headache grading stuff when I've got instead of a single multi-page file, it's multiple single-page files that I have to grade. So that's a pain. And then we want to do it with your phone and figure out a way to submit it to Canvas from your phone. So we'll see how that works out. Those will be relatively simple assignments, but it is something that I want you to learn. So otherwise, I will see you tomorrow and be watching for a
do you know when the projectile motion lab is going to be out?
Maybe by later today.
All right, and it'll be due about next week or so?
Yeah, probably, what day is today? Tuesday? Probably around next Tuesday, I think.
Right.
Although you will have to get together with your teammates on that. And I'm splitting you up into teams, and I'll let you know on that. But the sooner you jump on that, the better off you'll be. You'll want to contact those people. And I think you have a people tab on your Canvas page, don't you, where you can look at the other people in the class, I think. If you didn't, I'll put it up there. You'll be able to message them and do that. And I'll set up a separate Zoom meeting for every group. So you can arrange to meet, say, okay, let's talk about this Thursday afternoon at such and such a time. And then you can have your own Zoom meeting and talk about this. So that's how it'll work anyway. Okay, but be watching for that. And if you have questions, let me know. So I will talk to you tomorrow.